Hello and welcome to Mysteries of Earth. Today we journey into one of the deepest questions ever asked. How could nothing exist before the Big Bang? For centuries, we've tried to trace our origins back to a single moment of creation, a universe bursting into existence out of emptiness. But was it truly nothing? Or was it a hidden reality beyond space and time, a quantum foam, a multiverse, or even pure consciousness waiting to awaken? In this video, we'll explore the mysteries of cosmic origins, from string theory and higher dimensions to eternal inflation, the holographic universe, and the haunting question of whether true nothingness can ever exist at all. If you enjoy journeys into science, mystery, and the unknown, make sure to subscribe to Mysteries of Earth and join us as we uncover the hidden truths of our universe. What does it mean to ask, what existed before the Big Bang? It is a question that resists answers yet refuses to be silenced, a question that feels both inevitable and impossible. To ask it is to press against the edges of human thought, to look past galaxies and time itself into a silence so complete that even language begins to collapse. For most of human history, nothingness was a concept wrapped in philosophy and myth. Ancient cultures imagined creation as a kind of emergence from chaos, a void that was not truly empty but alive with potential. In Greek mythology, it was chaos, the yawning gap from which everything poured forth. In Hindu cosmology, it was the timeless waters in which Brahma dreamed the world into being. Even in Genesis, creation begins with a formless void. But the modern scientific picture makes the question sharper. Physics suggests that 13.8 billion years ago, the observable universe expanded from a state of unimaginable density and heat. Space itself began to stretch. Time itself began to tick. The Big Bang is not an explosion in space. It is the expansion of space. It is not the detonation of matter into emptiness. It is the very beginning of the framework in which matter, energy, space, and time can exist at all. And here the paradox emerges. If time itself began with the Big Bang, then what could it possibly mean to ask what happened before it? The very word before loses meaning at the boundary. It is like asking what is north of the North Pole, a question that seems logical but dissolves under its own weight. Yet we ask it anyway, because deep down we feel that something must have come before. Our minds recoil at the idea of true nothingness, of a reality without context, without origin. We search for causes, for chains of events that link one moment to another, but when we reach the Big Bang, the chain breaks. The foundation itself gives way. Philosophers call this the problem of first cause. If every effect must have a cause, what caused the first effect? If the universe is an unbroken story of events, what was the opening line? Some traditions answer with the divine, a creator that stands outside of time beyond cause and effect. But science seeks natural explanations, patterns that can be tested and traced. And so physics and cosmology wrestle with the question in their own language. To do that, we must first explore the concept of nothing, because not all nothings are equal. One kind of nothing is philosophical, an absolute absence, where there is no matter, no energy, no space, no time, no laws, no potential, no possibility. This is the purest form of nothingness, the kind most people imagine when they hear the word. But here's the problem. Such a state may not even be possible. Modern physics suggests that even the emptiest vacuum is not truly empty. It seethes with quantum fluctuations, with virtual particles flickering in and out of existence, with uncertainty woven into its very fabric. In the quantum world, even nothing does not stay. Nothing for long. Another kind of nothing is relative. Compared to the infinite expanse of space, the void between galaxies feels empty. Compared to the mass of a planet, the vacuum of interstellar space feels like nothingness. But even this emptiness is filled with faint radiation, with passing neutrinos, with fields that stretch across the cosmos. So which nothing are we talking about when we ask what came before the Big Bang? The philosophical nothing, the physical vacuum, or some deeper, stranger state of potentiality that we have no language for? Science approaches these questions carefully, not because it fears them, but because it respects their complexity. When cosmologists trace the history of the universe back to its earliest moments, they can describe events with astonishing precision. The birth of protons, the formation of light elements, the moment when the universe cooled enough for atoms to form. They can describe the glow of the cosmic microwave background, the fossil radiation left over from when the cosmos was just 380,000 years old. But when they try to push further, back to the first second, the first fraction of a second, the first instant, their equations begin to collapse. General relativity predicts a singularity, a point of infinite density. Quantum mechanics resists the idea. Each theory works beautifully on its own, but together they clash. And it is at that clash, that crack in our knowledge, where the impossible question lives. What came before the Big Bang may be beyond the reach of current science, or it may be the key to the next great revolution in physics. Some propose that the universe is cyclical, that before our Big Bang there was another universe, contracting into itself only to be reborn. Others suggest that our universe is just one bubble in a vast multiverse, inflating endlessly, spawning new universes like foam on a cosmic sea. Still, others propose that time itself is emergent, a property that arises from deeper laws, like temperature arises from motion. In such a picture, asking what came before time may be meaningless, and yet the question will not die, because in the silence before the beginning, we sense something more than absence. Perhaps it is our own need for origins. Perhaps it is the whisper of truths we are not yet ready to name. The paradox of nothing challenges us because it exposes the limits of our thinking. We are creatures of time, bound to causes and effects, to beginnings and endings. But the universe may not play by these rules. Its origins may be stranger, subtler, and more profound than any story we can tell. And so the question remains, what does it mean to ask what existed before the Big Bang? Perhaps it means that we are staring at the boundary between science and philosophy, between knowledge and wonder. Perhaps it means that in seeking nothing, we are really seeking ourselves, and our place in a cosmos that may never reveal its ultimate origin. This is the impossible question, the one that begins not with answers but with silence, the one that invites us to step deeper into the mystery, where every attempt to explain brings us closer, yet also farther away. And it is here, at this boundary, that our journey begins. What if the universe is not a one-time event, but part of an eternal rhythm? Not a single story with a beginning and an end, but a symphony of endless verses, expansions and contractions, deaths and rebirths, a cosmos that is both mortal and immortal at once. This is the idea of the cyclic universe, the notion that our Big Bang was not the first, and will not be the last. It is a vision that stretches back into the oldest myths of humankind. Ancient Hindu cosmology imagined the universe as a cycle of creation and dissolution, vast cosmic days and nights, each lasting billions of years, as Brahma breathes in and out. The Stoics of ancient Greece believed the cosmos was destined to burn in fire and be reborn again, endlessly repeating its history. Even in Norse mythology, the cycle of Ragnarok destroys the world only for it to emerge anew, reshaped but alive. These stories were poetic guesses at truths that modern physics now dares to explore. Because in the mathematics of cosmology, cycles may not just be myth, they may be woven into the very fabric of reality. The modern cyclic vision begins with the problem of endings. If the universe continues to expand forever under the push of dark energy, it drifts toward heat death, a state of maximum entropy, where all stars fade, all structures dissolve, and nothing new can ever form. An eternal silence. But what if that is not the final word? What if expansion does not last forever? What if gravity eventually reclaims its dominance? In such a scenario, the universe would slow, halt, and reverse. Galaxies would begin to fall inward, drawn together in a collapsing cosmos. Temperatures would rise, densities would grow, and in the end all matter and energy would compress back into a single blinding point, a big crunch. From that singularity, a new big bang might ignite. The end would seed the beginning. The cosmic story would loop endlessly, without need for an absolute start. This was one of the earliest scientific cyclic models, a simple seesaw between Big Bang and Big Crunch. But it raised new puzzles. Would each new cycle be identical to the last? Or would each rebirth carry new possibilities, new laws, new histories? If the universe had truly existed forever, how many times has this story played out before? And how many times will it again? Modern theories add richer detail. Some physicists propose that each cycle stretches the universe larger than before, like a cosmic heartbeat that grows with every pulse. In these ekpyrotic models, inspired partly by string theory, our universe is a kind of three-dimensional membrane floating in higher dimensional space. When it collides with another membrane, the energy of the impact ignites a new Big Bang. The result is a series of universes, each born from collisions in a hidden higher reality. Our cosmos would be only one frame in an infinite film strip, playing on without end. Others imagine a universe that never reaches absolute singularities at all. Instead, quantum gravity might prevent infinite compression, creating a bounce. The universe contracts down to a small but finite size, then rebounds, expanding once more. If so, the Big Bang was not the beginning, but simply the most recent bounce in an eternal cycle. Time itself could stretch backward through infinite expansions and contractions. No first moment, no final curtain, just the eternal swing of the cosmic pendulum. Even entropy, that great arrow of time, may not stop the dance. Some cyclic models propose that as the universe expands toward emptiness, dark energy dilutes entropy by stretching it thin, resetting the cosmic state for the next cycle. Others suggest that black holes, instead of erasing information, might pass it along into the next rebirth, ensuring that nothing is ever truly lost. The implications are staggering. If reality is cyclic, then perhaps our universe has lived and died countless times before. Every galaxy, every star, every planet, every life echoed across endless eons, written and unwritten again and again. Are we unique, or are we fated to repeat ourselves in every cycle? Or do cycles branch into new variations with different histories unfolding each time? The cyclic cosmos forces us to confront the strange possibility that eternity is not a straight line but a circle, that the universe is not headed toward nothingness but toward renewal, that death itself, on the largest scale, may be only transformation. But these ideas also come with mystery. We have not yet seen the universe slowing. Observations show that dark energy is accelerating expansion, not halting it. If this trend continues, the big crunch will never come. Does that mean cycles are an illusion? Or does it mean that our current cosmic epoch is just one stage in a larger, more subtle rhythm we have not yet glimpsed? Some physicists suggest that dark energy itself may change over time. If its strength weakens, gravity could eventually overcome expansion, bringing collapse. If its strength grows, it could trigger a catastrophic big rip, tearing space itself apart, a violent ending that might paradoxically seed a new beginning. Others speculate that quantum processes could recycle universes even in an eternally expanding cosmos. In an infinite sea of time, fluctuations could spawn new big bangs from the ashes of the old. Each rebirth would not require a collapse, only the restless creativity of the vacuum itself. And then there is the question of memory. If cycles are real, do they carry traces of the past? Could the patterns of galaxies, the faint signals in the cosmic microwave background, contain echoes of universes before our own? Some researchers search for such imprints, scars in the sky that might whisper of cycles gone by. Nothing conclusive has been found, but the search itself reminds us how deeply the question touches our desire to know where we came from. The cyclic cosmos is both comforting and unsettling. Comforting because it suggests that nothing is ever truly lost, that every end gives rise to a new beginning. Unsettling because it implies that our universe is not singular, but one of countless iterations, none of them final. In a cyclic universe, immortality is not promised to individuals, but to the cosmos itself. And so the vision of eternal loops brings us back to the mystery of origins. If cycles are endless, then perhaps there was no first cause at all. Perhaps the universe has always been rising and falling, breathing in and out forever. But if cycles themselves evolve, if each rebirth is different from the last, then perhaps even eternity has a story, a direction, a purpose we do not yet see. The idea of the cyclic cosmos stretches human imagination to its limits. It asks us to see the universe not as a straight road with a beginning and an end, but as a wheel turning endlessly through creation and destruction. And it leaves us with a haunting thought. What if this has all happened before and will happen again forever? The rhythm of eternity is difficult to hear, but if it exists, it means the Big Bang was not the first note in the cosmic symphony. It was only the latest, and the music may never end. What if the deepest truths of the universe are hidden in places we cannot see? What if reality itself is woven from structures smaller than atoms, vibrating threads of energy resonating across dimensions curled beyond our perception? This is the promise and the mystery of string theory. For most of human history, the world seemed simple. Space had 3 dimensions: length, width, and height. Time was the 4th, flowing steadily forward. Together they formed the stage upon which all events unfold. It was Einstein who revealed that this stage is not rigid, but dynamic. Space-time, bending under the weight of matter and energy. His vision reshaped physics, uniting space and time into a single fabric. But string theory dares to suggest that this fabric is richer still, that the universe is not confined to the 4 dimensions we know, but expands into realms we cannot see. Extra dimensions, folded tightly upon themselves, hidden like intricate patterns rolled into the threads of reality. Why would the universe need more than 4 dimensions? The answer lies in the quest to unite the 2 great pillars of physics: general relativity, which describes the vastness of gravity and space-time, and quantum mechanics, which governs the subatomic world. On their own, each works with astonishing precision, but together they clash. Attempts to describe black holes, the Big Bang, or the very fabric of space at the smallest scales run into contradictions. A deeper framework is needed, one that can contain both. String theory proposes that the fundamental building blocks of reality are not point-like particles, but tiny, one-dimensional strings. These strings vibrate in different modes, much like the strings of a violin. And just as each vibration of a violin string produces a distinct musical note, each vibration of a fundamental string gives rise to a different particle, electrons, quarks, photons, even the graviton bump. The hypothetical quantum particle of gravity all emerge from the symphony of these vibrating filaments. But for the mathematics of strings to work, the universe cannot exist in only 4 dimensions. The equations demand more. In the simplest versions, 10 dimensions are required, 9 of space and 1 of time. In others, 11. These extra dimensions are not wide and open like the 3 we know, but curled up into shapes so small that we cannot perceive them directly, like a sheet of paper rolled into a cylinder. From a distance it seems 2-dimensional, but up close a hidden circular dimension is revealed. The shapes of these hidden dimensions, known as Calabi-Yau manifolds, may determine the very laws of physics. The way strings vibrate depends on how the extra dimensions are folded, just as the acoustics of a violin depend on the shape of its wooden body. In this view, the particles and forces of our universe are not arbitrary. They are the echoes of geometry far smaller than any microscope can see. This idea opens unsettling possibilities. If the hidden dimensions can take many forms, then perhaps there are countless possible universes, each with its own physics, each shaped by the folds of its unseen dimensions. Our cosmos could be just one solution among an infinite landscape of realities. But string theory does not stop there. In some formulations, our universe itself is a 3-dimensional brain, a membrane floating in a higher dimensional space. Everything we see and touch is confined to this brain, like ink upon a sheet of paper. Yet beyond it, across dimensions we cannot access, other brains may drift, and sometimes they may collide. In one version of the cyclic universe, the ekpyrotic model, the Big Bang was not the birth of space from nothing, but the aftermath of such a collision. 2 brains, after eons of drifting, struck one another, unleashing energy and igniting the cosmos we inhabit. If this is true, then our universe is but one in a greater multiverse of brains, endlessly moving and colliding in higher dimensional space. The thought is almost impossible to grasp. A universe within a universe, dimensions beyond dimensions, existence built from strings so small that trillions could fit within a proton. Yet, this is the strange beauty of string theory. It suggests that the vastness of the cosmos and the tiniest scales of reality are not separate, but deeply connected. Still, the theory remains controversial. For all its elegance, string theory has yet to produce definitive, testable predictions. The extra dimensions are too small to see. The strings themselves are far beyond the reach of our most powerful accelerators. Critics call it untestable, more philosophy than physics. Supporters argue that it is the most promising framework we have for unifying the laws of nature. Perhaps the universe hides its deepest truths in ways we are only beginning to imagine. What would it mean if string theory is correct? It would mean that reality is music, that every particle, every force, every atom, star, and galaxy is a note played on the strings of the cosmos. It would mean that the universe is a vast symphony composed across hidden dimensions, resonating through time. It would also mean that the story of the Big Bang may not be one of creation from nothing, but of geometry unfolding, of brains colliding, of strings vibrating into being. Our cosmos may not be unique. It may be one melody among countless others in a higher dimensional concert. The mystery, of course, remains. We cannot yet see these hidden dimensions. We cannot pluck the strings of the universe directly, but mathematics has led us here, whispering that reality is stranger, deeper, and more beautiful than our senses suggest. And so the question lingers, are we inhabitants of a simple 4-dimensional world, or are we shadows cast by a grander structure, living in a reality richer than we can perceive? The search continues, only through mathematics, through experiments at the edge of possibility, through the imagination that dares to see beyond the visible. Perhaps one day we will glimpse the hidden dimensions. Perhaps we will find evidence that our universe is not alone, but part of a vast multiverse of brains and strings. Until then, string theory remains a reminder that the true nature of reality may be far stranger than the human mind was ever built to comprehend. From the ancient myths of rebirth to the modern visions of hidden dimensions, one theme endures: that the universe is not what it seems, that beneath the surface lies a deeper order waiting to be discovered. And as we leave behind the vibrating strings and folded dimensions, another question arises, one that carries us to the next frontier. If our universe is part of a multiverse, how do we fit within it? Are we an accident of cosmic geometry or something more? What if our universe is not alone? What if everything we see, every star, every galaxy, every cluster of matter stretching across billions of light years, is just a single bubble floating in an endless cosmic sea? This is the idea of eternal inflation, a vision of reality where universes are not rare but inevitable, where creation is not a singular event but an ongoing process, universes budding into existence without end. To understand this possibility, we must begin with inflation itself. In the early 1980s, physicists faced a puzzle. The Big Bang explained the expansion of the universe, but not its startling smoothness. No matter where we look, the cosmos is nearly uniform, galaxies scattered in roughly the same density, cosmic background radiation evenly spread across the sky. How could distant regions, separated by vast gulfs of space, appear so similar when light had not had enough time to travel between them? The answer came in the form of a radical idea, that in the first instant after the Big Bang, the universe underwent a sudden burst of exponential expansion. A trillionth of a second when space itself ballooned outward faster than the speed of light. This inflationary epoch would have stretched any initial irregularities smooth, leaving behind the uniform universe we observe today. Inflation solved the mysteries, but it also opened a door to something far stranger. Because if inflation can happen once, why not again? In fact, according to the mathematics, inflation may never completely end. Regions of space may stop inflating, condensing into bubble universes like our own. But beyond their boundaries, inflation continues, endlessly creating more bubbles, more universes, each with its own birth, its own laws, its own destiny. This is eternal inflation, a cosmic engine forever producing new realities. In this picture, our universe is just one bubble in an infinite froth. Beyond the edge of our observable cosmos, countless other universes are born. Some may look like ours, with stars, planets, and life. Others may be utterly alien, ruled by different physical constants, where atoms cannot form, where light behaves differently, where time itself may flow in ways we cannot imagine. The possibilities are staggering. If the laws of physics vary across these universes, then the values we take for granted, the charge of the electron, the strength of gravity, the speed of light, may not be fixed, but local. Our universe's particular recipe of laws may simply be one possibility among many. And here lies one of the most profound questions of all. Why do the constants of our universe seem so perfectly tuned for life? The strength of gravity, for instance, is balanced so delicately that if it were slightly stronger, stars would collapse into black holes before they could nurture planets. If it were weaker, stars would never ignite. The nuclear forces that bind atoms are tuned so precisely that even the smallest shift would make chemistry and life impossible. In a single universe picture, this fine-tuning is a mystery, sometimes explained by chance, sometimes by design. But in the multiverse, it becomes inevitable. If infinite universes exist, each with different constants, then most are sterile, but in some, the conditions just happen to allow complexity, chemistry, and consciousness. And it is only in those universes that beings like us can ask the question at all. In this way, the multiverse offers an explanation for the apparent perfection of our cosmos. We live in a universe tuned for life because life could not exist in any other. Our bubble seems special, but only because it is one of the rare bubbles where observers can emerge. Yet this answer is both comforting and unsettling. Comforting because it explains the improbable. Unsettling because it suggests we are not privileged, but ordinary, one flicker of awareness in an infinite ocean of possibilities. If eternal inflation is true, then reality is far larger than anything we can observe. The observable universe, with its hundreds of billions of galaxies, may be just a speck in a greater cosmos that stretches beyond imagination. A cosmos where the birth of universes is as natural as the birth of stars. But how could we ever know? Other universes, by definition, lie beyond our horizon, unreachable by light. Direct observation may be impossible. Still, some physicists suggest subtle clues might remain. Perhaps collisions between universes could leave imprints in the cosmic microwave background. Perhaps gravitational waves could carry whispers of events beyond our bubble. The search continues, though the evidence remains elusive. And so we stand before a profound possibility. Our universe may be infinite in itself, or it may be one among infinitely many. It may be unique, or just one note in an eternal symphony of creation. The thought stretches the human mind to its limits. If the multiverse is real, then every possibility may be realized somewhere. Worlds where stars burn blue and cold, worlds where life never arose, worlds where history unfolded differently, branching into paths we will never see. What does it mean then to live in a multiverse? Are we diminished, knowing we are not unique? Or are we elevated, knowing we are part of a reality so vast that it deifies imagination? The multiverse does not offer easy answers. It challenges the way we think about existence itself. If there are countless universes, each with their own laws, then ours is not the final word on reality. It is one perspective among many, a reminder that what we see may be only the smallest fragment of what is. And perhaps that is the greatest gift of the multiverse, not certainty, but humility, a reminder that the cosmos may be larger, stranger, and more wondrous than our minds can comprehend. The story of eternal inflation leaves us with a vision of bubbling universes, endlessly born from the fabric of space. But this raises an even deeper question. If new universes are constantly being created, then what lies at the foundation? What is the ultimate fabric upon which all these bubbles emerge? To answer this, we must look to the very limits of physics, to the Planck epoch, the quantum foam, the seething frontier where space and time themselves dissolve. Imagine standing at the very edge of knowledge. Not at the boundary of a continent or the horizon of the sea, but at the limit of what human thought can describe. Beyond this threshold lies a place where our mathematics shatter, where our theories collapse, where the very language of science refuses to go further. This place has a name. It is called the Planck epoch. The Planck epoch represents the earliest moment of the universe we can meaningfully speak about. It begins not even a blink after the Big Bang. just 10 to the minus 43 seconds after time itself supposedly began. A fraction so small it defies comprehension. To put it in perspective, if you compared 1 second to the entire age of the universe, and then divided that second into trillions upon trillions of pieces, you would still be nowhere near the brevity of the Planck time. It is the smallest meaningful unit of time, a boundary beyond which our equations lose their grip. At this scale, the familiar picture of the cosmos dissolves. Space-time itself, the smooth stage upon which all events unfold, is no longer continuous. Instead, it is thought to be granular, broken into discrete units like the pixels of a screen. Scientists call this the quantum foam, a restless sea of microscopic fluctuations where space and time boil and froth in violent unpredictability. It is a realm where Einstein's theory of general relativity, our best description of gravity and the geometry of space, collides head-on with quantum mechanics, which governs the subatomic world. Each theory works flawlessly in its own domain, but at the Planck scale they refuse to cooperate. Relativity demands smooth curves and continuity. Quantum theory insists on randomness and discreteness. When we try to merge them, infinities explode out of the equations as if reality itself is telling us, you cannot go further. Not yet. This is the wall of knowledge, the point where our scientific tools crumble in our hands. And yet, we are certain that something was happening there. The entire universe, all energy, all matter, all space, was compressed into a region smaller than a subatomic particle. The densities and temperatures were so extreme that the very concept of before becomes meaningless. Asking what came before the Planck epoch is like asking what is north of the North Pole. Time itself had not yet stabilized into the flowing river we experience. The Planck epoch is not just a physical barrier, but a conceptual one. It is the place where before and after dissolve. Some physicists describe it as a kind of cosmic veil. On our side of the veil, the universe has a story, a sequence of events, a history we can reconstruct. On the far side, there may be truths about existence that lie forever hidden, not because we are not clever enough, but because the universe itself does not allow those questions to be asked. And yet, human curiosity refuses to stop here. We reach for tools that might pierce the veil. One of these tools is the search for a theory of quantum gravity, a single framework that would unify relativity and quantum mechanics. Candidates exist: string theory, loop, quantum gravity, and other attempts to weave a consistent picture of reality's smallest scales. Each proposes a universe where space-time itself has structure woven from loops, strings, or discrete chunks of geometry. If these ideas are true, then the Planck epoch was not chaos, but something even more profound, a place where the building blocks of space-time itself were assembled, a moment when the very fabric of reality crystallized out of some deeper, unknown order. But what was this deeper order? Some imagine that the Planck epoch was the residue of a prior universe, a remnant left behind by a cosmic cycle of birth and collapse. Others suggest that it was a quantum fluctuation from nothing, a seed sprouting from a vacuum that was never truly empty. Still others propose that it was a transition between states of mathematics, a moment when the rules themselves emerged from timeless patterns. What unites all these ideas is the recognition that at the Planck scale, our universe touches mystery. It is the place where existence itself becomes a question. Even the language we use begins to fail us. When we speak of time, we imagine a line stretching forward and backward. But at the Planck epoch, the line breaks into fragments. When we speak of space, we imagine a smooth expanse, but here the expanse frays into foamy fluctuations. Our metaphors collapse, and yet we must use them because they are all we have. And so scientists turn to mathematics, to abstractions that transcend ordinary thought. They imagine space-time as a network of nodes and links, a web of relationships more fundamental than geometry. They imagine energy fields vibrating in higher dimensions, their harmonies giving rise to particles, forces, and even time itself. But perhaps the most humbling lesson of the Planck epoch is not what it tells us, but what it denies us. It reminds us that there may be limits to human knowledge, that reality may possess layers forever beyond our comprehension, that our greatest theories may be no more than shadows on the wall of a deeper truth. Still, this wall is not a dead end, it is a frontier. Standing before it, we are invited to wonder, to ask not only what the universe is, but why it is intelligible at all, why mathematics can describe galaxies and atoms, but falters at the moment of creation, why existence begins with a question it cannot answer. The Planck epoch, then, is both a mystery and a mirror. A mystery because it hides the ultimate origin of our cosmos. A mirror because it reflects our own limitations back at us. And yet, there is beauty in the not knowing. For in the silence beyond the Planck wall, imagination flourishes. Here, science brushes against philosophy. Here, equations become poetry. Here, we are reminded that the cosmos is not just a machine to be explained, but a mystery to be experienced. As we leave the Planck epoch behind, we do so with humility. We do not know what came before, or if before even makes sense. But we know that on the far side of that wall, something extraordinary occurred, something that gave rise to the expansion of space, to the birth of particles, to the unfolding story of galaxies and stars, something that led, in the end, to us. And now, having reached the very edge of time, we turn to another frontier, one not of the past but of the future. If the Planck epoch is the wall that hides our beginning, then what lies ahead in the far future of the cosmos? Will the universe expand forever into silence, or collapse into fire, or transform in ways we cannot yet conceive? To answer, we must journey from the birth of time to its possible ends. What is the universe made of? The ancient answer was simple: earth, air, fire, and water. Later, we refined it into atoms, protons, quarks, and fields, but today a stranger answer whispers through the equations of physics. Perhaps the universe is not made of matter at all. Perhaps it is made of information. Everywhere we look, the universe behaves less like a solid machine and more like a vast system for processing data. The stars are not just burning spheres of gas, but records of fusion and collapse. The rocks beneath our feet are not just minerals, but archives of Earth's 4.5 billion year story. Even our own DNA is not simply a molecule, but a library, an intricate code storing the instructions for life. This perspective grows from a principle so profound that many physicists believe it may be the deepest law of all: information is never destroyed. Imagine burning a book. To the eye, it seems the information in those pages has vanished forever. But physics insists otherwise. Every letter, every sentence is encoded in the ash, in the smoke, in the rising heat and drifting photons. If one could track every particle released by the fire, in principle the entire text could be reconstructed. The information never dies, it only changes form. This law, the conservation of information, is as central to nature as the conservation of energy, and it leads to staggering implications. If information is indestructible, then every event that has ever occurred in the cosmos still exists in some hidden form, encoded in the quantum structure of reality itself. The birth of stars, the fall of civilizations, even the private thoughts of every living being, all of it preserved forever in the deep mathematics of the universe. But where is all this information stored? This is where one of the most revolutionary ideas in physics enters the picture, the holographies principle. Inspired by the paradoxes of black holes, it proposes that the true information content of the universe is not written inside it, but on its surface, on a distant boundary that encloses all of space. The story begins with black holes. These cosmic abysses seemed, at first, to be destroyers of information. Anything falling beyond their event horizons, a planet, a star, even a library of books, appeared to vanish without trace. Stephen Hawking himself once suggested that black holes erase information permanently, but this idea shattered the foundations of physics. If information could be destroyed, the very fabric of quantum mechanics would unravel. Then came a revelation. Jacob Bekenstein and later Hawking discovered that the amount of information a black hole contains is not proportional to its volume, but to its surface area. The information is encoded on the horizon, like data on the surface of a cosmic hard drive. Over eons, as the black hole evaporates through Hawking radiation, the information leaks back into the universe. Nothing is ever truly lost. If this is true for black holes, might it also be true for the universe itself? Physicists began to wonder, what if the entire cosmos is a kind of hologram? What if everything we see in 3 dimensions is actually a projection of information inscribed on a 2-dimensional surface at the edge of space-time? It sounds like science fiction, but the mathematics is compelling. Our universe might be like a cosmic hologram. The 3-dimensional reality we inhabit emerges from patterns of information encoded on a distant boundary we cannot directly see. Just as a holographic image carries depth from a flat surface, our reality may carry matter, energy, and time itself from this hidden informational frontier. This idea does not diminish reality, it deepens it. It suggests that the truest essence of existence is not matter or energy, but the relationships between things, the flow and storage of data. Reality is not the stage and the actors, but the script, the information that makes the play possible at all. If this vision is correct, then even consciousness might be understood in informational terms. The thoughts in your mind, the memories that define you, the awareness that is listening to these words, all of it could be seen as patterns of information dancing on the quantum fabric of space-time. And because information is conserved, some trace of this pattern may never vanish, even after your body fades. This way of seeing the cosmos blurs the line between physics and philosophy. It asks us to think not of the universe as a cold machine, but as a cosmic archive, a place where nothing is ever truly forgotten, where every photon of light carries a record of its journey and every interaction writes a permanent entry in the ledger of reality. And if the holographic principle is true, then the question of what existed before the Big Bang takes on a new form. Perhaps the answer lies not in matter or energy, but in information itself. The Big Bang may not have been the beginning of everything, but the moment when information from a prior state was re-encoded into the new fabric of space-time. Our universe, then, could be the latest chapter in an eternal informational process, one where beginning and end are just shifts in how the data is written. This vision of the cosmos is hauntingly beautiful. It suggests that the story of existence is never erased, that what you are, what we all are, is not just temporary matter destined for decay, but part of an eternal record inscribed into the deepest structure of reality. but it also raises unsettling questions. If reality are misinformation, who or what reads it? If the universe is a hologram, what lies beyond the screen? And if information is indestructible, then what happens to the story of consciousness after the last star dies? We stand then at the threshold of a new way of seeing. The universe is no longer simply matter and energy expanding through emptiness. It is something richer, stranger, and perhaps more enduring, an ocean of information weaving itself into the form of galaxies, stars, life, and thought. As we move forward, we confront a deeper and more disturbing possibility that this information-rich universe, as stable as it seems, might itself be fragile. That the very vacuum we rely upon as the backdrop of existence may be unstable, ready to collapse into something entirely different. If that day comes, the laws of physics themselves could be rewritten in an instant. And so we leave the idea of information behind and step into the unsettling possibility of the cosmos ending not with a whimper, but in a sudden and silent catastrophe. What does it mean for something to come from nothing? It is one of the oldest questions in philosophy and one of the strangest in science. We imagine nothing as an empty void, a blank canvas, silent and still. But in the language of quantum mechanics, such a void does not exist. There is no perfectly smooth, featureless nothingness. There is only quantum nothingness, a restless sea where silence itself trembles and where existence flickers in and out of being. At the heart of this lies a principle so radical it reshaped physics in the 20th century, the uncertainty principle. It tells us that certain pairs of properties, like position and momentum, or energy and time, cannot both be known with perfect precision. The universe forbids it. And because of this rule, a true vacuum, a state of absolutely zero energy, is impossible. Even the emptiest space must carry uncertainty, and that uncertainty manifests as fluctuations. These fluctuations are not metaphors. They are real, measurable, and everywhere. In the apparent void between stars, in the darkness of intergalactic space, even in the vacuum of a laboratory chamber, particles appear and vanish constantly. They are called virtual particles, brief, ghost-like entities that wink into existence, borrow energy from the vacuum, and then dissolve back into nothingness in time so short they defy comprehension. This activity is not just theoretical, it has consequences we can measure. The Casimir effect, for example, arises when two uncharged metal plates are placed extremely close together in a vacuum. The fluctuations of virtual particles outside the plates differ from those between them, creating a measurable force that pushes the plates together. It is as if the nothingness itself is alive, exerting pressure. Quantum nothingness, then, is not empty at all. It is a field of infinite potential, a stage where possibility itself plays. And this brings us to one of the most daring ideas in cosmology, that these fluctuations may not only give rise to particles, but to entire universes. Consider the quantum vacuum on a cosmic scale. If fluctuations can create particles for a fleeting instant, could they also create something larger? In certain models of cosmology, the answer is yes. A fluctuation in the fabric of space-time itself could, in rare circumstances, inflate into a self-sustaining universe. From the perspective of physics, there is nothing forbidden about this. Our universe itself may be the result of one such quantum accident, a fluctuation that did not collapse back into silence, but expanded, inflated, and became everything we see today. This vision radically reframes the question of origins. The Big Bang may not have been the first cause in a chain of logic, but rather the byproduct of quantum uncertainty, the ultimate something, born not out of design, but out of the impossibility of true nothing. If this is true, then nothingness is the most fertile ground of all. The void is not barren, but pregnant with potential. It is a womb that endlessly spawns new realities. And our universe, galaxies, stars, life and thought, is but one fleeting blossom in an infinite quantum garden. But what does this say about meaning? If our cosmos is just one of countless fluctuations, a lucky accident among endless possibilities, then is our existence trivial or miraculous? One could say both. For while universes may emerge without end, this particular one is tuned with exquisite precision. The values of its constants, the balance of its forces, the very possibility of life, all flow from the physics of that first fluctuation. A delicate accident, yes, but one that carries within it the weight of everything we call reality. The idea unsettles. It suggests that the most fundamental question, why is there something rather than nothing, may dissolve upon inspection, because nothing, as we imagine it, does not exist. There is only a quantum restlessness that ensures something must always flicker into being. In this sense, existence is not the exception, but the rule. And yet, mysteries remain. Why do fluctuations follow the patterns they do? Why does the quantum vacuum have the properties it has? If the uncertainty principle forbids nothingness, then what forbids the uncertainty principle itself? We arrive at the edge of comprehension, where the language of mathematics still hums, but the melody of meaning falls silent. Even so, the insight is profound. It teaches us that emptiness is never empty, that silence is never still, and that nothingness is not an abyss, but a foundation, a fertile soil from which universes grow. From here, our journey deepens. For if quantum fluctuations can create worlds, then what of the hidden patterns beneath them? If reality itself emerges from probabilities, are we living inside a grand equation, a cosmic code, or even a simulation? The next frontier is not only about the birth of universes, but about the very fabric of what it means to be real. And so from the trembling of the void, we step toward the even stranger possibility that our universe is not simply born from nothing, but written, stored, and computed like information in a cosmic system beyond our imagination. Does the universe need us to exist? It is a question that seems almost arrogant, as though human awareness could influence the vast machinery of the cosmos. And yet, in the strange world of quantum physics, the role of the observer cannot be dismissed so easily. At the heart of the puzzle lies the measurement problem. Quantum theory describes particles not as things, but as probabilities, waves of possibility that stretch across space and time. An electron, before we look, does not sit in one place. It exists in many places at once, was spread out in a shimmering cloud of maybes. This is called the wave function. But the moment we observe, measure, or interact with that electron, something astonishing happens. The wave function collapses. The possibilities vanish, and a single reality crystallizes. The electron is suddenly here and not there. This phenomenon raises a haunting question. Would that reality have existed without an observer? In everyday life, the collapse seems automatic. Detectors, instruments, even particles themselves appear to play the role of observer. But when we press deeper, the boundaries blur. What does it mean to observe? Does the act of measurement require consciousness, or is it simply an exchange of information? For decades, physicists have wrestled with this mystery. Some argue that consciousness has no special role, that the collapse of the wave function is a physical process, needing no observer in the human sense. Others, however, point to a stranger possibility that awareness itself may be fundamental, woven into the fabric of reality. This interpretation echoes through history. The physicist John von Neumann argued that only the conscious mind could complete the act of measurement. Eugene Wigner went further, suggesting that consciousness might not only register reality, but actively create it. To these thinkers, the observer effect T was not just a feature of quantum mechanics. It was a clue that mind and matter are deeply entangled. If true, this would transform our understanding of the cosmos. The universe would not be a cold machine grinding forward indifferent to us. Instead, reality itself would be participatory, shaped by the act of perception. But how far does this idea go? Some interpretations reach into the very history of the cosmos. The physicist John Wheeler proposed what he called the participatory anthropic principle. In this view, consciousness does not simply observe a universe that already exists, it plays a role in bringing it into being. Like a quantum experiment stretched across time, the universe's history may not be fully real until it is observed. Wheeler even speculated that our measurements today could retroactively give reality to the earliest moments after the Big Bang. Imagine this: the cosmic microwave background, the fossil light of creation, exists as a probability field until measured. And by observing it now, billions of years later, we collapse that ancient wave function, giving the early universe a definite past. In this sense, the act of looking backward defines what was. It is a radical vision, one that suggests the universe and consciousness are not separate, but locked in a strange loop of co-creation. The cosmos produces life, life produces observers, and observers in turn give meaning to the cosmos. Skeptics push back, and rightly so. Consciousness is one of the least understood phenomena in science. To claim it shapes reality risks replacing mystery with speculation. Most physicists prefer interpretations that leave awareness out of the equation, attributing collapse to interactions between systems rather than to the human mind. Yet even in these cautious views, the measurement problem remains unresolved. Why does probability become reality? A mechanism decides when the wave function collapses, and so the door remains open. Consciousness lingers at the threshold of physics, neither fully excluded nor fully explained. If we take the idea seriously, the implications ripple outward. Could the universe itself be conscious in some way? Might reality be less like a machine and more like a mind? Some theories in neuroscience and physics propose that consciousness may be a fundamental property of matter, as intrinsic as space or time. In this light, the universe is not a dead stage on which awareness emerges as an afterthought. It is a living field in which consciousness and existence arise together. We are left then with a paradox. On one hand, we are small, fragile creatures on a pale blue dot, adrift in an immense cosmos. On the other, our act of seeing, of measuring, may be indispensable to the very reality we inhabit. We may not be passive witnesses, but participants in the unfolding of the universe. Does the universe need us to exist? Perhaps not us, specifically, but perhaps it needs something capable of observation, of reflection, of consciousness. Perhaps awareness is the mirror in which the cosmos sees itself, and without that mirror, reality would remain a haze of probabilities, never resolving into form. And so we stand before a mystery deeper than any equation. What is consciousness? Where does it come from? And how, if at all, does it bind itself to the quantum world? These questions lead us beyond physics alone into the borderlands of philosophy, neuroscience, and even metaphysics. For now, all we can say is this: the act of observation is not trivial. It is the hinge on which probability becomes actuality. Whether this requires our minds or simply our presence as physical systems, the result is the same. The universe is not fixed until it is experienced. From the quantum laboratory to the edge of the cosmos, we find a strange suggestion. Perhaps the story of the universe is incomplete without us. Perhaps reality is not just out there, waiting, but in here, unfolding through the act of awareness. And so we step forward from the question of consciousness to the deeper puzzle it reveals. If observation gives reality form, then what does that say about the hidden order beneath it all? Could the universe at its core be less about matter and more about meaning? Less about particles and more about patterns? In the next chapter, we explore the possibility that the cosmos itself may be a grand code, a reality built not of substance but of symbols, where information is the ultimate foundation. What will become of everything? It is the ultimate question, not of our species or our planet or even our galaxy, but of the universe itself. The cosmos has lived for 13.8 billion years, but like all things, it must face an end. The stars that light our skies are temporary beacons. The galaxies that wheel across the void are fleeting structures. Even space and time, vast as they seem, may not last forever. To imagine the universe's fate is to confront possibilities that stretch beyond human imagination, destinies both majestic and terrifying. Physicists outline 4 great scenarios for how the cosmos might end: the heat death, the big crunch, the big rip, and vacuum decay. Each one paints a radically different portrait of the future, and each one hinges on a mysterious force that shapes the universe today: dark energy. Dark energy is the invisible hand driving cosmic expansion. Discovered in the late 1990s, it revealed that the universe is not slowing down as once thought, but accelerating outward. Space itself is stretching faster and faster, as if propelled by an unseen pressure, and the nature of this force will decide our ultimate fate. The first possibility is heat death. If dark energy continues its quiet work, galaxies will drift farther apart until their light can no longer reach one another. Stars will burn out, leaving behind black dwarfs, neutron stars, and black holes. Over unimaginable timescales, even those remnants will evaporate through processes like Hawking radiation. The cosmos will grow thin, cold, and silent. In this vision, the universe does not end in fire, but in ice. A dark eternity where entropy reaches its maximum and no structure remains. The second scenario is the big crunch. If dark energy weakens, gravity may eventually reassert control. Galaxies would slow, halt, and begin to fall back toward one another. Over billions of years, the universe would collapse inward, heating as it shrinks. Stars would ignite in a final cosmic blaze as matter compresses into an ever-denser fireball. In the end, all of space and time would converge into a singularity, a mirror image of the Big Bang, but in reverse. From this furnace, perhaps a new universe might one day emerge. The third fate is more violent, the Big Rip. If dark energy grows stronger, its repulsive force could overwhelm every bond in the universe. First, galaxies would be torn apart, then solar systems, then planets, then atoms themselves. Even the fabric of space-time would shred in the final moments. The cosmos would not die slowly, but be ripped to pieces in a cataclysm of unimaginable violence. And then there is the most unsettling possibility of all: vacuum decay. Quantum physics suggests that our universe may not be in its most stable state. It may be resting in a false vacuum, a precarious valley in the energy landscape of reality. If so, a single quantum event could trigger a collapse to a lower state. A bubble of true vacuum could form, expanding at the speed of light, erasing the laws of physics as it sweeps across space. In an instant, everything, matter, energy, time itself, would vanish, replaced by an alien reality governed by entirely different rules. Each of these destinies is terrifying in its own way. Each reminds us that the universe, vast and eternal to our eyes, is also fragile, contingent, and impermanent. But is this the whole story? Must existence end in silence, collapse, or decay? Some thinkers imagine alternatives. Perhaps intelligence, once it arises, can shape the cosmos itself. Theoretical physicist Freeman Dyson once speculated that advanced beings could adapt to an eternally cooling universe, slowing their thoughts and actions to match the thinning trickle of available energy, stretching consciousness into infinity. Others envision civilizations harnessing dark energy itself, bending the expansion of the universe to their will. Still others wonder if minds could escape into new universes, seeding the multiverse with sparks of awareness that outlive their parent cosmos. And beyond these speculations lies an even deeper question. Could consciousness itself survive the death of the universe? If awareness is fundamental, not derivative, if it is part of the basic fabric of reality, then perhaps it need not vanish even when stars go dark. Perhaps it will endure in forms we cannot yet conceive, echoing across whatever comes after. What is striking is this. Even when we contemplate the cold equations of entropy, expansion, and decay, we find ourselves drawn back to life, to mind, to meaning. We ask not only how the universe will end, but what that ending will mean for us, for the fragile spark of consciousness that the cosmos has, for now, brought forth. So we look into the deep future and see many possibilities: a frozen eternity, a fiery collapse, a violent tearing, a sudden erasure. And yet, through them all, lingers the question of whether something, awareness, information, or perhaps even a new beginning, might endure beyond the end. For if the universe had a birth, why not a rebirth? If space-time itself can emerge once, why not again? And if consciousness is truly woven into the story of reality, then perhaps it will not be silenced, but will find its way into the next chapter of existence. The fate of the universe is the fate of everything we know: galaxies, stars, atoms, and thought. It is the final horizon of science and thought, a deepest mystery of philosophy. To ask how it ends is to ask what it all means. And so, from visions of collapse and decay, we turn toward the final paradox, the haunting possibility that the universe may not be as it seems at all, that what we call reality may be a shadow, a projection, a story written in code. The last mystery may not lie in the stars, but in the very nature of existence itself. What if nothingness is not the absence of everything, but the beginning of everything? We often imagine nothing as a barren void, a silent emptiness without time, space, or possibility. But what if this image is wrong? What if nothingness itself is alive, not with matter or energy, but with potential, with awareness, with the seeds of universes yet to be born? It is one of the strangest and most unsettling possibilities in science and philosophy, that consciousness and nothingness are not opposites but companions, that the emptiness we fear at the edges of existence may in fact be the ultimate creative force. Throughout history, we have tried to separate mind from matter, the observer from the observed, the human story from the cosmic one. But the deeper we push into the frontiers of physics, the harder it becomes to draw such clean lines. Quantum mechanics has already shown us that observation and reality are intertwined, that the act of measurement shapes the world it measures. Perhaps the same principle holds at the largest scale of all. Perhaps the universe itself exists because consciousness looked into the void. Imagine the quantum vacuum, the so-called nothing from which particles appear and vanish. To the eye of classical physics, it seems empty, but quantum physics tells a different story. The vacuum teems with fluctuations, with restless energy, with endless uncertainty. It is never truly still. What if this vacuum is more than a sea of randomness? What if it is the first faint stirring of awareness itself? A conscious nothingness that does not merely allow reality to exist, but chooses it into being. Some physicists and philosophers have dared to imagine such a thing, that consciousness is woven into the very foundation of reality, not as an afterthought of biology, but as a primordial presence. In this view, the vacuum is not dead space. It is a fertile ground of mind, a creative silence that births universes the way a tree produces leaves, effortlessly, eternally without end. Could this mean our universe is not an accident but a design? Not in the narrow sense of a blueprint drafted by some external architect, but as the natural flowering of awareness itself. Just as thought gives rise to ideas, perhaps consciousness gives rise to cosmos, the laws of physics, the values of constants, the emergence of stars, galaxies and life. All of it could be the unfolding expression of a deeper intelligence rooted in the fabric of nothingness itself. This is not the design of human myths, where the universe is created once and finished. It is design as process, as experiment, as play. Every new universe could be a question asked by the conscious vacuum. What if gravity is stronger? What if time flows differently? What if matter and mind intertwine in new and astonishing ways? Across countless cycles, countless bubbles, countless realities, consciousness explores itself by becoming worlds. Here, the boundary between science and philosophy begins to blur. Eternal inflation, string theory, the holographic principle, each points toward a reality far larger than what we see. And yet, beyond the equations, we glimpse a deeper pattern, that existence seems tuned, not random, participatory, not indifferent. The constants of nature balance on knife edges that allow complexity, chemistry, and consciousness. Why should this be so? Some argue it is chance, multiplied across infinite universes. But another possibility is that these values are not accidents, but outcomes of a deeper principle, that consciousness itself shapes the stage on which it will later awaken. This would mean that mind and cosmos are not separate, but aspects of one eternal creative process. The universe gives birth to consciousness, and consciousness gives birth to universes in an endless loop. Matter becomes mind, mind becomes matter, and the circle completes itself again and again. Perhaps this is what nothingness truly is, not absence but wholeness, not a void but a womb, a fertile silence in which all possibilities rest, waiting for awareness to call them forth. If so, then asking what existed before the Big Bang may be like asking what exists before thought. The thought and the thinker are not two, but one. The bang and the awareness that allows it are inseparable. Our universe is not an object floating in emptiness, but an expression of emptiness that is conscious of itself. And what does this mean for us? Fragile beings staring out into the cosmos, trying to understand. It may mean that consciousness is not merely a byproduct of matter, but the very thread from which matter is woven. That when we look into the night sky, we are not just seeing stars and galaxies, but the reflections of a deeper mind, one that includes us within it. In this light, the fate of the universe is no longer a story of inevitable decay or destruction, but of transformation. Even if galaxies drift apart, even if stars burn out, even if space-time itself dissolves, the conscious nothingness from which it all arose remains. And from that silence, new realities will bloom. Perhaps we are participants in this process. Perhaps every act of awareness, every flicker of thought is part of the same cosmic creativity that ignites universes. The cosmos becomes aware through us, and we become real through it. The circle closes and opens and closes again, forever. The story we have traced from the first moments of time to the farthest futures returns us to its beginning. But the beginning is not emptiness. It is not nothing in the way we once thought. It is a conscious nothingness, alive with potential, with creativity, with the eternal possibility of becoming. So when we ask what existed before the Big Bang, perhaps the answer is not nothing, but everything, not in the form of stars and galaxies, but as the silent awareness that gives rise to them all. And in that realization lies the deepest mystery of all, that the universe and consciousness may not be two separate things, but one, eternal, inseparable, and endlessly creating itself.